Okay, so today we are going to start section 9.3, where we are going to construct confidence intervals for the cases where we don't know the standard deviation, which is most of the time is the case anyway, unknown standard deviation, because since we don't know the mean of the population when we are trying to estimate the mean, when we are trying to find differences between means, the standard deviation, I mean, you don't know mean, but you know standard deviation. That case in section 9.2 may not be so realistic. It may only be realistic when you have, for example, a measurement error for a device or something. But yeah, this is this is saying it's valid. We may know the variance if it's given by the manufacturer as some kind of an error of the measurement device. But more often, so this 9.3 is a more popular case. The population variance is unknown. And then what we do is we're going to estimate it from the sample, just like we have an estimate for the mean. So in the case of large samples, it's not going to be very different actually. The methods that we use for when we have a large sample, and again, this definition of large may be vague. As I said, 30 may be used as a rule of thumb to determine whether it's large, but maybe 30 may not be large for certain cases as well. It may be 100, it may be 200, but for example, 500 is large, okay? But yeah, in this semester, in this course, you may assume anything that is larger than 30. If you assume it's a large sample, you won't be penalized for any points for that in the exam if you consider samples that are larger than 30 to be large. So when we have a large sample, we don't need to know the population variance. We can use our estimate, which is the sample standard deviation. Sample standard deviation can be used so this sample of the standard deviation of our sample can be used as our standard error. So we estimate standard error by sample variance, and we use that instead of the sigma that is given to us. Okay, so here again, when we say that we use an estimate of theta hat, sometimes in the question, whatever your estimate is, the standard error of your mean may not be given. All right, so it may be again, it may be the standard error of the individual samples that are given to you. So that's a really important distinction. Okay, here when we say we are using an estimate for our sample, here we estimate the standard deviation of our sample and use that for the population variance as an estimate for that. It's one thing I want to note as very important is that this the one that is given in the question, for example, if you look at this example 9.16, the early sample has a mean delay time of 0.8 seconds with a standard deviation of 0.1 seconds. So this 0.1 is not directly the standard error. So it's not what you're going to directly put into the equation. 0.1 is the standard deviation. It's the sample standard deviation. It still refers to the standard deviation of those individual variables you have. So when your estimate is for example, for the mean, if your goal is to estimate the mean of or to find the difference between means of two populations, you're going to be using this 0.1 and you have to divide it by the square root of the sample size. Remember, we had this sigma divided by square root of n, right? So here, this the one that is given in the question, sample standard deviation, replaces this one. So the standard error of your estimate, for example, if it is x bar, the standard error of x bar, you have to use the sample standard deviation given in the question, okay, so this is the sample standard deviation in the question that is given to you. Again, you need to divide it by the sample size because that sample standard deviation is given for individual variables, whereas this x bar is the sum is an average of those individual variables in which its standard error is going to be computed. Again, with this formula, the standard deviation of the sample that is given in the question replaces this sigma. Okay, this is really critical. It's I mean, it may be misleading as you read this section that okay, this is the sample, this standard error is not the same as sample standard deviation. Okay, so as you can see, we did not directly use 0.1 here as the standard error for x bar. The standard error, actually our theta hat here in this case is the difference between two means, x bar minus y bar. Okay, so its standard error is computed by using the sample standard deviation and squaring it, dividing it by this sample size, the same for the other sample, and taking the square root. So this entity here on the right hand side is this standard error, standard deviation of our estimator, which is computed as we did when the population variance was known. Okay, so this, I need to make this very clear that this Sx here that is given in the question is not the standard error. It's the sample standard deviation, and it still refers to the standard deviation of individual variables, individual measurements. Okay, in the case of large samples, it's really, you will be given a case if you read the example text. For example, 500 packets are sent through the same network between 5 p.m. and 6 p.m. This is sample X. And 300 packets are sent between 10 p.m. and 11 p.m., sample Y. So we collect two different samples at different time intervals, 500 and 300. These are large numbers. The early sample has a mean delay time of 0.8 seconds with a standard deviation of 0.1 seconds. So this is the delay time, mean delay time for individual packets, and this is the standard deviation of that delay time for an individual packet. And this is the second sample with the X bar and S, the sample standard deviation. So construct a 99.5 confidence interval for the difference between the mean delay time. So this is really a high confidence. As you can see, the high confidence, it's 2.81 standard errors. We have to, if you want to have more confidence, you have to have more of the area. 99.5 of the area is so here we want 99.5% of the area contained under this. So here this becomes 2.81 and minus 2.81 in standard normal distribution. In standard normal distribution, in other words, the phi, the cumulative distribution for 2.81 is equal to 99.5 plus something, right? If I say 99.5, it's not correct. So half of the area is to this side. So 99.5 plus 0.25, right? So this is what that 2.81 is in the cumulative distribution function for the standard normal. Right, so we have to, if you go this much to the right, you're going to have 0.25% because the remaining is 0.5%. 0.25% is here and 0.25% is here. So we want to have our confidence interval to include 99.5 of that distribution. So therefore you have to go, this was the difference, 0.3. You have to go 2.81 standard errors away from the center, which is 0.3. So when you construct this confidence interval, you're very confident that, as you can see, the confidence interval contains all positive values here. The delay in the packets between 5 and 6 p.m. are significant, is larger, we can say. The delay, we observe more delay between 5 and 6 p.m. compared to 10 and 11 p.m. All right, so as you can see, this is the same confidence interval building that we did when we know the standard deviation. The only thing we replaced was the sample variance replaced this. So this was a simple example. Now, the other interesting part, this unknown standard deviation, we haven't talked about a case where for estimating population proportions, for example, this percent of, for example, 1% of Turkish people have blue eyes. That's you want to build a confidence interval, for example. I mean, this is a hypothesis that I made, but if you want to, for example, build a confidence interval of 99% confidence, that what is the percentage of Turkish people who have blue eyes? Okay, if you want to do that, you collect a sample, for example, 1,000, a sample of size 1,000. But here, the thing that it's not the mean. You're not looking for a mean, like the average height or average age. It's a proportion that we're trying to figure out. So each individual random variable in this case is like a Bernoulli variable, right? I mean, it's each x eyes here, you either have blue eyes or not. So it's either zero or 1. In this case, in that sense, the sample mean of those 0 1s will be a good estimate for the population proportion. What proportion of the population satisfies that condition is a member of that event. So that's called confidence intervals for proportions. And here the interesting thing is that why didn't we, let me ask you a question. Why didn't we discuss this confidence intervals for proportion in section 9.2, where the variance is known? Okay, so don't we know the standard deviation in this? So why do we have this confidence intervals for proportion in the section where we don't know the variance? Does anybody have any idea about this? So in other words, can we know the population variance when we are trying to estimate the proportion? Think about the Bernoulli variable. The Bernoulli variable, think about the parameter it has, the success probability, right? Think about the success probability in a Bernoulli variable, which is P. It has only a single parameter. And our goal is to try to estimate P. It may be possible that you know the standard deviation, but you don't know the mean in a normal distribution, in any other distribution, right? Because the population parameters, the distribution parameters may not be directly inside that X bar and variance. But in Bernoulli, what was the variance in Bernoulli variable? If we have the single parameter P, the proportion or the success probability, this is what we are trying to obtain, right? The proportion, this P is the same as the success probability. So this, what I'm asking is this first sentence of this section. Why don't we, why it says in particular, we surely don't know the variance when we estimate a population proportion. Why is this the case? Why don't we know the variance? It says this is something obvious. This is what the first sentence say. Do you see why it is obvious? Or this is what I'm trying to ask here. That's the case because, it may not be very easy at first, but in a Bernoulli variable, the variance of a Bernoulli variable x is equal to, if you remember, it's p times 1 q, which is p times 1 minus p, right? If somebody gives you that the population variance is, for example, 0.25, if I tell you the population variance is 0.5, if standard deviation is known, if population variance is known, what does this tell us? it tells us that p is equal to 0.5, right? Because if this is given to us, if somebody tells you population variance is 0.25, then there's only one unknown in this variance formula, which is this p. If this is given to you, you just say p1 minus p is equal to 0.25, and then you immediately solve for p, which is 0.5. And by the way, this is the largest the variance can get. But if for any other values of this, you will immediately know p. So if we know p, I mean, if we know variance, it means that if we know the proportion that we're trying to estimate. So if we know that already, why do we try to estimate it? So that's basically what this first sentence is saying. If your goal is to estimate population variance, population proportion, it means that you also don't know the variance, because if variance was known, then the population proportion that you're trying to estimate is also known directly from the variance. That's why this confidence intervals for proportion is in this section where we don't know the population standard deviation. We don't know this. This variance is unknown to us, therefore this is therefore in this section. So here the indicator, if each of these, let's come back to this, what percentage of Turkish population has blue eyes, if we think about that. Each of those individual people, individual data point in our sample will be this indicator variable, which is a Bernoulli variable. If it is, if somebody in your sample has blue eyes, xi is 1, otherwise it's 0. So therefore here the expected value of your individual variables will be p, and the variance is given like this. So this is given from the question. So our estimate that the average, if you just take the average of those ones and zeros, it will give you an estimate for the population proportion. Okay, so we just count, we look at the frequency of blue-eyed people in our sample, and we use that as an estimate for the p, the success probability, the proportion in the Turkish population with the proportion of people with blue eyes. That's our p hat. So here, since we don't know the variance, we use again an estimate for our variance. What we are going to be using is this. The variance of p hat is going to be equal to p times 1 minus p divided by n. So since this is an average, as you can see, p hat, this is the standard error. Our standard error will be the square root of this thing. Since here, by the way, we don't know what p is, by the way, we are going to be substituting p hat as an estimate for p, also for the standard error. So first of all, if you look at this part of the text, basically is saying that it's an unbiased variable. It's asymptotically normal, since it's a summation of many random variables. It's asymptotically normal for large samples, and it's unbiased because its expected value is also equal to this. If by using linearity of expectation, you can figure that out. And we are going to construct the confidence interval for p. We don't know the standard deviation. The standard error is unknown to us directly. So what we do is we use the estimate. The standard, this is the actual standard error, but this is, we cannot know. Because p hat is these variables divided by n. So in the variance formula, again, because of linearity of expectation, we divide this by n. So this p times 1 minus p is the variance of those individual variables. Okay, so it's like this. The summation of all these variables, because of linearity of expectation, the variance of the sum is going to be n squared. So it's like n times, let me write it again here. So it's the same formula that we did earlier. Okay, so what is the variance of n times x, okay? It's n square x, right? This is the variance of n times x. So this is the variance of the sum. But the thing is that we are not interested in the variance of the sum. We divide this by a number, okay? Which is, so actually then the standard deviation of this would be, the standard deviation of this will be n this, the standard, not x actually. I should write this. If the individual standard deviation of x is this, and the standard deviation of x, therefore, standard deviation of this summation is going to be the square root of this thing. Let's call standard deviation of n times x is going to be the square root of this thing, which is n times the square root of this. And since this is not the sum, but the average that we're looking for, the average is found by dividing this by. So this was, did I do it correctly? No, yeah, it's, if you do, you have to again divide it by n square. So this is how, this is not the sum we're looking for. We're looking for, so what here, what, when we do it like this, first we figure out how many we figure out the standard variance of the sum, which is this, and then the standard deviation of the sum is going to be equal to n square root of this thing. And since we are going to be dividing again this, so it's, let me just show you the third section again, this table quickly. So let's see why it was like that. Right, linearity of expectation, expectation of a function, covariance, yeah, right here. So here, the variance of a sum comes from here. So the variance of the sum is this. So if we're, the average here, okay, is this one divided by n. So here, I think it was right, and in the beginning of section 9, that we use the sigma divided by square root of n function. Let me see right here. So standard error, not this one. Oh, it was a section, chapter 9 actually. Yeah, here. So when we have a standard error of something like this, so the here it comes from here. When we are looking at the average is divided by n. So it was sigma divided by n. That's why we divide the variance by n. Okay, so it's the variance of the average, not if it was the variance of the sum itself, the variance of the sum. So x1 to xn, if we have n times of these variables, n times xi, the variance of that will be n square, the variance of that individual variable. So if this is the variance, the standard deviation is going to be n square root of n, and we divide, sorry, square root of, this is directly sigma, by the way, n square sigma square, that's the variance of individual variable. Variance was sigma square. Okay, so this one divided by n square gives us, so these cancel out. That's why the variance of the average is sigma divided by, sorry, this is directly sigma divided by square root of n. So this was sigma squared, it's not square root of sigma. So sigma divided by square root of n comes from the average value here It's the standard error, standard deviation of the average, not the sum. That's why we divide it with that. And I think it was also here too, the standard error, when we're computing the standard error. So let's see where we had there. Yeah, here, the standard error of X bar is individual standard deviations divided by square root of n. So therefore, the variance is divided by n. Standard deviation is the square root of variance. Therefore, we have the square root of n coming from here. So the variance of X bar is equal to, therefore, I mean, if you just take the square of this thing, it's sigma squared divided by n, right? So this follows from linearity of expectation. Also here as well. All right. So let me come back to 9.3. Yeah. So if we the proportion here, we were looking at the proportions. It's not here. Come back to 9.3. Went too far away. Yeah. So it means that since this is this is the same thing. So the standard deviation of a Bernoulli variable. What is the standard deviation of a Bernoulli variable? P times 1 minus P. Okay, so this is the standard deviation, in other words, sigma of a Bernoulli variable. So divide this by square root of n, you get your standard error for X bar, which is your P hat. Okay, so this P hat is our standard error. So this is basically the square root of this thing is equal to the standard error of X bar. This is the standard deviation of X bar. That's why we divide it by this. So the problem here is that in the formula for standard error, it contains P. If we don't know P, we cannot compute the standard error. That's why this one is saying standard error is unknown. We don't know the standard error. So the standard deviation, this standard error is unknown. So if you look at the standard error, this is standard deviation of individual variables divided by square root of n. So this one is unknown. We try to estimate this. What we need to do is we use an estimate for p hat, so which we get our population proportion. You collect your sample. You look at how your frequency of the item data points in your sample that contains that variable. That's your p hat. So your standard error is also computed from the estimate p hat in this case. Okay, so basically, in general, the confidence interval for a population proportion will be whatever you estimate here, plus minus your confidence significance level, your alpha. You use the same z alpha over 2, and this becomes your standard error. So let's, again, for the same thing when we are doing for difference between two proportions. For example, if you want to compare two things, this may be in an election. Election is a good example. For example, a political party gets this many votes, another political party gets this many votes. The votes that the political parties get, they are like proportions of the population. So if you want to, for example, figure out what is the construct the confidence interval for the difference between the votes these two political parties get, the proportions, the percentages. So anything about the percentage of the population, that's a proportion. So you can also do the same thing. Your estimate is the difference between these two proportions, this for what you're interested in. And it may be estimated by difference between these two proportions. Therefore, it's standard error, again, just like you did for the general population of mean, as we find the confidence interval between two population means. Again, we add the standard errors of these individual variables. Again, this follows from linearity of expectation, And the variance of this thing, although there's a minus in front of it, since the variance of a times x is a square x, so again from linearity of expectation, this becomes a summation. The, the variance of this difference is the summation of those individual variances, and we take the square root of that to get the standard error. And again, the standard error contains the two unknown proportions in it. We use our estimate P1 hat and P2 hat to do that. This tells us that in order to do something about population proportions, we need to have large samples. If we don't have large samples, using P1 hat and P2 hat for the for building confidence interval is not going to make sense, right? So when you're doing for population proportions, you have to have large samples. Otherwise, the variance is unknown. It will be very difficult. I mean, your confidence interval estimate will not be good because your standard error is computed using the proportion you have, proportion estimate you have in the sample. So and this is the difference between two populations. This is the standard, this is the variance of that individual proportion. This is the variance of the other proportion. You add the variances, its square root gives you the standard error of your estimate, which is the difference between these proportions. So let's look at these examples. A candidate prepares for local elections. During his campaign, 42 out of 70 randomly selected people. So 70 is our sample size here in town A. And we have another town and we collect a sample of size 100 from that other town. And 59 out of, so these are our estimates, estimated P1 and P2 in this case are 42 divided by 70. That's our proportion in town A. And 59 out of 59% or 0.59 is the proportion in town B. Estimate the difference in support that this candidate is getting in towns A and B. So does this candidate have a better support in town A or town B? What is the difference between the supports this candidate have in these two towns? Basically, we are looking for P1 hat minus P2 hat. Whatever this 42 divided by 70 is, let's see, 42 divided by 70 is 0.6. And the other is 0.59. So they're really close actually, 0.6 and 0.59. So build a 95% confidence interval. Here, the difference is just 0.01. As you can see, they're really close. And the standard error in this case will be, it was 0.6 in one town. So P times 1 minus P gives us 0.6 times 0.4 divided by 70. So if we don't divide by 70, you're going to get this variance of the sum, not the proportion. So the variance of the standard deviation is going to get smaller and smaller. It gets smaller with square root of n. It means that if you get more samples, you're going to have lower variance. Okay, so it's also intuitive why we divide by square root of n. So this entire thing is the standard error of the difference between P1 and P2 hat. And if we multiply the standard error with 1.96, which is z alpha over 2, z alpha 0.025 here, it's 1.96, which means that 2.5% of the population is to the right-hand side of 196 in the standard normal distribution. So this is the widely used value we have seen earlier, 1.96. So if you add and subtract this many standard errors from the difference here, you see that it's between minus 0.14 and plus 0.16, which means that the difference with 95% confidence, the support in town A may be lower or higher. Okay, so it's 0 is like almost at the center of this. So we may say that we may not claim that it has higher support. So this 0.6 being larger than 0.59, with 95% confidence, we cannot for sure say that the support in um, town A is larger than the support in town B. We don't have significant evidence to show that, basically. So this is what we usually say. The obtained data does not indicate affirmatively that the support in town A is stronger. So it can be less strong or more strong. So if you look at this confidence interval, so you're not uh, affirmative. We cannot say we never say for certain, but we cannot significantly say that it's town A has more support. In town A, the candidate has more support than town B. Okay, so this is, we are going to see hypothesis testing, which is going to also have something. We are going to be doing things like these. We are going to be making hypotheses. For example, the hypotheses will be the candidate has more support in town A. We are going to build the null hypothesis and the alternative hypothesis. And similar to this confidence interval test, we will be then, by looking at the sample we have collected, we will say, for example, there is significant evidence that town A has larger support or not. Okay, or we don't have significant evidence to show that. It may be inconclusive. We will say that the sample is inconclusive for the hypothesis that says this candidate has more support in town A. Now, here is an interesting subsection, estimating proportions with a given precision. Remember, we talked about sample size versus margin earlier. If you want to, here, yeah, let me get your question in this example. So, do we support in town? Yeah, exactly. With 95% confidence, we are 95% confident that the support in town A may be 14 points less or 16 point more. Okay, so this is basically saying it's either this or that. So it's not very conclusive, as you can see. We cannot be very affirmative. It's either 14 percent points less or 16% point more than in town B. With 95 point, we are 95% confidence. In that we can say that. Okay, so what you have written is correct. It's either 14% points less or 16 points more than B. Yeah, and we're 95% confident in that. But you may be very confident, 95% confident, but the statement itself is a very vague statement, right? It's like either you win or you lose. Of course, either you have more support in town A or you have more support in town B. That's obvious, right? So what you're stating here is that you have less or more confidence in town A, and I'm 95% confident in that. Actually, you could easily be 100% confident in that, saying that these are only the two options, right? You're either less or more support. So this is therefore this doesn't tell us, but the units themselves, 14 points, 16 points, that means something. Actually, it's not the same as saying you're less support, more support. It tells us something. The difference is between these numbers. It's not that much. It's in between those 30% points. Our unit, the standard deviation of the standard normal distribution. So here are the standard error of the difference in this case is this. Okay, so it wasn't 0.15. The standard error between the difference we have in our case is, if you divide this by 196, that's the standard error of the difference. Okay, so the standard deviations of the difference between these two things. Let me use the calculator for that. So it was 0.15, right? If you divide 0.15 by 196, so this is 0.076. So this number here is the standard error. So so you get yourself here 0.01 as the difference, but its standard deviation of this is actually 0.07. It's even, it fluctuates a lot. This basically tells us that, okay? And it's if this sample size was larger, for example, instead of 70 and 100 samples, if you have taken 700 and 1000 samples, this would surely be you would this confidence interval will be a shorter confidence interval, and it's something unitless in this case is the difference. It doesn't, and also the proportion doesn't have a unit. It's a proportion. It's just the frequency. So what we do here is that by writing it like this, we also it's a standard variable. We standardize it, just we did by subtracting from the expected value of it and dividing by the standard error. So here it becomes a standard normal variable, not because it's a standard, it's a proportion. It becomes a standard random variable because we do this, just like we did earlier. The reason we multiplied with z times the standard error of this, it's the standard deviation of p hat. So we use the same formula that we use for building confidence intervals. Okay, so it becomes standard normal. It becomes standard normal distribution because of this. We standardize it because p hat is from the central limit theorem. P hat here is a normal variable because p hat is a summation. It's an average of a large number of values, zeros and ones. So p hat is normal, asymptotically normal here. And when we standardize it by doing this, we make it standard normal. That's why we multiplied with this. Its actual standard deviation was 0.07, but we get one standard deviation. In order to get one standard deviation, we multiplied with this to make it a standard normal variable. Okay, again, it's the same thing here with it. We standardize it. A non-standard random variable, you move it to its expected value and you divide it by the standard error. This becomes z. This becomes the standard normal variable when you do that. And if it is, if you're asking whether the actual p hat is between these things, if it's unbiased, you can replace p here. The expected value of p hat becomes p, and the probability that p is in this interval that you build, as you can see, z times whatever z times the standard error of this thing becomes the margin that you're going to be doing. Okay, here let me get back to this one. If you want to, as I just told you, that if you want to decrease the margin here, so I hope my discussion answered your question, Aralf. So okay, you're welcome. So if you want to decrease the margin, you want to increase your sample size. So we have learned that in section 9.2. Now, when it tells you that the number of, for example, if you want to find this, imagine, for example, we want to find the difference between these two proportions in this example, not with the margin of 0.15, but if you want to decrease this margin of 0.15 to 0.01. You want to be really confident, okay, between the difference between not confident. Your confidence is still 95%, but with 95% confidence, you want to be more precise. You want to figure out, okay, this is not very precise, right? The difference between them was 0.01. And since our standard error was large, we cannot be very precise about this. The difference between the proportions is too large. It spans 0.30 of this possible potential difference of 2. Okay, the difference between them is one of them. Actually it's 1, right? The difference, if you get 0 support in one, the other is 1. The largest difference you can get is 1.0. And this interval, but that 1.0, this one can be smaller. So it may be 0, 1 or 1, 0. So it means that it spans actually the confidence interval spans the region between, its domain is between -1 and 1. So in this interval of size 2, this confidence interval we built spans 15% of it, an interval of length 0.3. It's not very precise. So if we want to be more precise with the same confidence, we want to decrease the margin. In order to decrease the margin, we need to increase the sample size. But here's the catch. What should be the sample size be? If you look at this formula we have here, the sample size n should be at least 700 or 100. For example, if I make, in this example, if I make it 700, 1000 or more, okay, you're going to decrease this, but what about the variance here? Do you think they're going to be still 0.6 and 0.4? No, right? Because these are 0.6 and 0.59. You don't know these beforehand. You only know it's 0.6. 0.6, remember, it's the sample proportion. You know it after you collect the sample. So we have a catch here, okay? It's like catch-22 situation, which is we don't know P. So therefore, if you look at the formula here again, in order to find how many samples you have to get for a fixed precision, this formula contains the standard deviation of those individual variables. You have to know the standard deviation. This is not the actual standard deviation, not the individual variables. This is the standard error. So you should know the standard error. But standard error we estimated by using population proportion. So we don't know the standard. So this is in section 9.3. We don't know the standard error. We can only estimate it from the sample. But you haven't collected your sample yet because you first want to figure out what size your sample should be. Should it be 1,000, 10,000? This is the first step. We want to first decide our sample size. But in order to decide the sample size, we don't know the variance. So what we do in this case is be conservative and saying that we just use the largest value this variance can get. The variance of a Bernoulli variable so we use here, actually I think this is the standard deviation. No, this n, this is not the standard error. This was the standard deviation of individual variables because this was this square root of n, sigma divided by square root of n was in this side of the equation. So this sigma is the individual sigma of the standard deviation of those individual variables. And we also don't know that. So this is p hat times 1 minus p hat. But since we don't know beforehand, this is a bad situation for us. But what we do is we assume the worst in this case. The worst case, this p times p 1 minus p, if you plot this function for all possible values of p, it becomes something like this. So it's this, okay? So this is the plot of p times 1. So this is sp changes from 0 to 1. So these are all the values a proportion can get between 0 and 1. And this is how the variance of the changes, the variance of individual variables, how they change as we move p from 0 to 1. As you can see, the highest value is attained as 0.25. So the variance, the largest variance we can get for a Bernoulli variable is 0.25. Okay, it's either 0 or 1. Okay, it only gets these two values, and the largest for any value of p, any success probability, the largest it's going to get is when it's like a fair coin, when we have heads or tails. If the p is equal to 0.5, that's where we get our largest variance, which is 0.25. So what we do is we use this 0.25 as our formula here in this. So instead of the sigma, we just use 0.25. Assume the worst. It cannot be worse than this. So this is like a conservative estimate of your sample size. Even if you don't know anything about p, let's assume the worst and let's assume the variance as large as possible, and then decide on your sample size. This is what we do in deciding on sample sizes for proportions. Okay, it was here. So the formula therefore becomes this 0.25 and should be as large as this. So if you take a look at this, so here sigma, so this sigma square is taken out. Sigma square is as large as 0.25. So in other words, you can just, sigma is 0.25 square root. I mean, you can take this out, sigma square out, and say 0.25 directly. So 0.25 times whatever confidence level you have here, z alpha over 2 divided by your margin. So if you want to figure out, let's try to compute it for our candidacy case. For example, if you want to find the same, the difference between those two populations with the same confidence, 0.95 confidence, but this time with 0.01 precision. Okay, so the difference between them, one of them was 0.6, the other was 0.59, okay, 0.59, and the difference between them was 0.01. And our precision in this case was not good, right? I mean, the difference is this small and this is our plus minus, so it's too much. If you want to increase your precision to 0.01, what should your sample size be? How many people you have to ask in those towns to have this? So what you need to do is this 0.01, 196 square times 0.25. So this is the number of samples should be at least this much. This is our margin, which is our precision, and this is our confidence level. So if you want to have more confidence, it's going to increase again. For example, if you want to increase your confidence, this number is going to increase, which means that you have to have more samples. If you want to decrease the margin, which means increase the precision, again, you want to increase the sample. But this 0.25 is our largest variance we can get. That's playing conservative. And let's take a look at this number. So this is 196 squared times 0.25. So it becomes 196 times 196. Divide that by 4. 9,600. Okay, so if you want to if you want to have the same sample, the same confidence, if you want to increase your precision, if you want to find this 0.01 difference with plus minus 0.01, you have to ask at least 9,600 people in those towns. Okay, that's the total number. So actually, in both of those towns. In both of those towns, you have to ask 9,600 1,600 people, because that was the common denominator in both cases, right? So therefore we need to ask that many people. So here, yeah, this is what we did for proportions, and this is what we're going to, we use the maximum value of the variance, which is 0.5, to estimate this. Now, before we jump onto small samples, so this concludes our discussion on proportions with large samples. When we have small samples and unknown standard deviation, we are going to now learn a new uh, distribution. They are not going they are not going to be normally distributed. This small sample, but if the individual elements are known to be normally distributed, again, this is important. This is the case where we have individual random variables. We know that they're normally distributed, but we don't know their standard deviation, or we don't know their mean. And when we're trying to estimate our mean, so this one here, look at the standardized variable. This is our standardized variable, right? Theta hat minus theta divided by standard deviation, our standard error. So for large samples, this was a normal variable. It was the ratio of two random variables. Why is it? Does it say it's a ratio of two random variables? Because the standard error itself is a random variable, because we estimated from the sample. The actual theta hat is also estimated from the sample, so it's like a ratio of two random variables. This was normal when both of the when it was large, okay? But for small samples, this no longer looks like a normal distribution. This is what is called student's t-distribution, and we are going to talk about this after the break. Let's have a 10-minute break until 10:47. Okay, I will stop recording now.